Welcome back. In this video, we'll be resuming our program of renormalizing the λφ4 theory. And we are actually now starting to calculate the one-loop contributions to that theory. So what I have seen so far is that we can rewrite these, the usual λφ4 Lagrangian, right, in terms of these physical quantities, right? This is defined as the physical mass of the particles for this theory. This is defined at the coupling constant, which is measurable at a particular point in parameter space, right? So in a particular scale, if you will, right? And when you do this change of variables using all these definitions I have down here, right? For the field, you renormalize the field, and then you get these new quantities, right? And these are called the counter terms, or these three new pieces of the Lagrangian, right? Because the rest looks very similar to the original one, with the exception that now we're talking about more physical quantities, right? And we have seen that these coefficients for the counter terms, sometimes we call them counter terms themselves by abuse of language, right? These guys show up at one loop, right? So these guys are all zero at 3 level. So now I want to calculate this, right? I want to have expressions for them and see what kind of physical consequences they'll have. Of course, the connection between these new variables and physical quantities is only established once I apply what we call the renormalization conditions, right? So, for instance, this guy, I mean, in fact, the full m square here will only be the physical mass because I'm imposing these two conditions on the full propagator of the theory, which say that this will actually be a pole in the full propagator of the theory, and this was and also fixing the residue of that pole. Same goes for the coupling constant, right? This is the condition that says that this lambda here, right? I'll define delta lambda so that the lambda here is the coupling constant of the theory at this particular point in the phase space, in the space of momentum in the theory, right? Now I'll be suppressing these renormalized labels here because I'm always working with the new Lagrangian in terms of these variables, and it's pointless to be carrying that around. Now I have to calculate these two functions right here, right? The 2-point function and the 4-point function for λφ4, because then I can use these conditions to get the counter terms. In terms of Feynman diagrams, these guys are defined like this, right? So this is the sum of all 1pi contributions to the 4-point function, right? I have defined this like this, so I call this one I gamma. This one was the term I gamma 1, where this 1 means it's order lambda to the power of 1, right? So it's the first perturbative contribution. All these guys right here are order lambda square. So I call this I gamma 2, and this is the gamma 2 that is showing up here in this condition. So it's one of the things I have to calculate. And I know that the counter term, this is the counter term, right? This is the proportional to delta lambda. This counter term, I know it's also order lambda square because there's a cancellation that needs to happen between the counter term and these 3 loop contributions here, right? And then of course there's more terms, but I'm stopping at lambda square for now. The second function, this 2-point function, is also the sum of all 1pi contributions, right, to the full propagator. And this one starts at order lambda to the 1. So I call this guy minus I m square. And of course, these signs and i's that come in front of it are all just convention, right? You find people defining them in other ways, right? And this is, I would call this just minus I m2 at order lambda. And of course, there are higher order contributions of order lambda square. You might worry at this point that I'm stopping my calculation so far. I'm only talking about things that go up to order lambda square in the 4-point function and order lambda at the 2-point function, right? Why are you stopping at different orders, you might ask, right? And the thing is that in the end, when I go and try to calculate some S matrix element, I'll have to multiply these guys, 4 full propagators here, right, to the 4-point function. And then after I do these multiplications, I'll have cross terms and all kinds of complications here. And thereafter I do this multiplication, I'll be careful and stop the whole thing at a particular order of lambda. Of course, it makes no sense to just pick parts of any order of lambda contributions, right? But so far I'm only worried about calculating the one loop contribution, so I have everything I need when I get to the point where I had to multiply these things. Right? So I'll start with this little guy right here, which seems the less threatening loop to calculate. Right? And let's see what we get and what kind of tools we have to use to calculate this one. To start this calculation, I'll define momenta here. So I have a total momenta going, which I'll call P. And of course I have to define some momenta running around the loop, and I call this one K. Right? And then the Feynman rules for lambda phi 4 tell me that this diagram is given by minus I lambda, right? The rule for the vertex. There's a symmetry factor of 2 because of this loop. I have to integrate over the momenta running on the loop. That gives me this d4k over 2 pi to the 4th. And of course there's the propagator in here, right? Which is given by I k square minus m square plus I epsilon. Remember that in these 1 pi contributions, I'm not including these propagators, right? They are never included in the 1 pi contribution, just these things that are intrinsically 1 pi here. So this is what I need to calculate. This integral diverges, right? There's a divergent part here. And in order to see that better, I'll use a little trick called the Wick rotation. If you don't remember what this is, we have explored this in depth in the Quantum Field Theory 1 videos, I think it's video 6, right? You can go there and take a look. We'll also do a more careful review of Wick rotations on the next video. For now, all I want to do is see how this integral behaves for big momenta. And that's easier to do if I do this rotation. So I just think of it for now as a changing variables, which it's fairly accurate description, right? So I'll just change the integral in k0 to an integral in k4, defined like this, right? That means that k square here, which in Minkowski space is just k0 square minus k vector square, becomes, right, if I change it here, this becomes minus k4 square minus k vector square, which I'll call minus k Euclidean square. And the reason I call this Euclidean is because if you look at this definition, you see it follows a Euclidean metric, right? It's just sum square of the parts. So this guy is positive definite, right? And that's why it's useful, right? The measure of integration just becomes, right, which is written in dk0 all the way to dk3, right, becomes now I dk1 all the way to dk4, right, which I'll call I d4k Euclidean. Okay? Doing that in the integral, my loop now becomes lambda over 2, because there was an I here that, in fact, I can conceal these two I's together, right? And then there's a third one coming from here, which I'll put here, d4k Euclidean over 2 pi to the fourth, ugly integral corrected, and this denominator just becomes minus k Euclidean square minus m square plus I epsilon, and then I can rearrange the signs here. Right? Let me just copy this part over here. Right? Bring this I outside. A minus sign from down here, and then I can just change the sign of everything here in the denominator. And of course, now that I'm integrating these guys in Euclidean space, the Euclidean momentum square is never negative, this is always positive, and never zero, right? So I can ditch the I epsilon. I don't need the I epsilon when I'm working in Euclidean space. The big advantage of doing that is that in Euclidean space, I can define spherical coordinates, right? I can write k Euclidean mu, right? Now mu goes to 1 to 4 in this space, right? Like a 4 vector that looks like this, right? Ka sine of omega. I'll need 3 angles, right? Sine of theta, cosine of phi. This is the first component. The second one will be Ka sine omega, sine of theta, sine of phi, and then Ka sine of omega, cosine of theta, and finally just Ka cosine of omega, right? And these angles are defined in these ranges, right? So Ka is positive or 0. Phi goes from 0 to 2 pi, and the other two go from 0, so omega and theta go from 0 to pi. And that means I can rewrite the measure of integration, so I can rewrite d for k Euclidean as k Euclidean to the cube, because it's a 4-dimensional space. The integral over the modulus of this vector, and the solid angle, the 4D solid angle, right? Which in this case is defined as sine cubed of omega no, not cubed, sine square of omega, sine of theta, d phi, d theta, d omega. And then if I substitute all of these in this integral, now I get, let me copy it. Now I get just delete the I epsilon here. This becomes minus I lambda over 2 integral of dk A K E cubed d omega over 2 pi to the fourth times this propagator. And just copy it here, right? And this is just dependent on the size of this vector, not on the angles. That means I can do the angular part easily, right? You can do all these integrals with these measures, and you'll find out that this will be just the integral of this guy, will be just 2 pi square. 2 pi square. So this becomes just minus I lambda over 16 pi square, because I did some cancellations between the 2 pi square and these factors here. Integral over from 0 to infinity over the size of the vector, K cubed over K E square plus M square, right? And now you can see the divergence, right? I can take this improper integral and rewrite it like the limit of some, this has dimensions of momentum, right, in natural units of energy. So you have some parameter, which I'll call lambda, going to infinity, right, of this integral right here, with upper limit lambda. And this upper limit is problematic, right? If you go near it, you can ignore this mass because this momentum is get big, right? And this integrand here will behave like Ke cubed over Ke square, which is just linear in Ke, right? And if you do the integral near the upper limit, right, you have something that depends. So our diagram here is going like something that is the limit of lambda going to infinity of this part times the integral of Ke, which will be near the upper limit, just lambda squared. This is the contribution from the upper limit. Of course, there's more parts. There are either finite or are diverging smaller powers of lambda. But there's a divergence here, right? That much is clear. The thing is, I cannot just disregard these infinity as non-physical and cut this all away and just throw everything away, because I might be throwing physical information away if I do that. Right? The important thing is to keep in mind is that while divergent quantities, right, cannot have physical meaning, right, this quantity might be subtracted from another divergent quantity. In fact, we know there will be a cancellation between this one and the counter term, right? And the difference between diverging quantities can be finite and physically meaningful. Right? You have to be very careful, right? We know that from other areas of physics. If you're calculating things that are blowing up, but if two things are blowing up at the same time, the difference between them might be physical. Right? So you cannot just throw this away. Right? You have to keep your infinities under control so that you can see how fast things are diverging and see if their difference is finite, and if there is any observable that depends on the difference between them, even if nothing can depend directly on these diverging quantities, right? In order to get these things under control, right, we have a method called regularization, right? This is a way, regularization is a way to modify a diverging quantity so that it becomes finite, which is what you have inside here, but you recover, of course, the divergence under some limit, which in this case is just taking lambda back to infinity, right? This recovers the original divergence. In fact, this is a very simple regularization here that we call cutoff regularization. I just stopped the integral at some upper limit for the momentum. This hard cutoff in the integral, right, is equivalent to making the following change in the integrand. You can keep your integral all the way to infinity, but you can change the integrand in this way, right? This is the original one in blue, right? And you can change for one that is the same as the original up to lambda and 0 afterwards, right? That this will be the same as cutting the integral up, right? And the thing is, two things you need to keep in mind. First is that on this part of the momentum space, there is no change, right? So I'm keeping my low, let's call this low energy physics, the same, no change here. But of course, my results now depend on this parameter lambda. One would hope that eventually you can get observables that are independent from this, because this is totally non-physical, right? But there is a physical reason we expect that to actually happen, right? What I'm doing here is changing the physics in a scale that is far, as long as I can put this lambda far away from my region of interest, where I'm doing measurements, where I'm trying to describe some physical system, right? You have this, again, this separation of scales argument, that anything that I do at this particular energy should not depend on information coming from systems that will be described by other theories. So essentially what I'm doing when I change my integrand like that is parameterizing my ignorance. I cannot really be sure that my theory will follow this blue curve so far away from the point where I'm testing it, right? So that in a sense is what I'm trying to do here. I'm parameterizing my ignorance and then try to define observables that don't depend exactly where this lambda is. Right? This hard cutoff regularization here, it's useful in some cases, but it's not the one we are using. And the main reason is that it breaks explicitly translation in this momentum space, right? I cannot translate momentum now because there's a hard cut up there, right? And that might make things really awkward, right? Suppose down the line you're doing your calculations, you have to do changing variables here, and you need to shift this momentum. Then having something that breaks these translation invariance is really awkward. So we're going for something more sophisticated. The important thing to realize is the reason why these integrals are diverging, right? Essentially, you have to compare the powers of momentum in the numerator with the denominator, right? So even if you have, let's say we're doing an integral to infinity here, the lower limit does not matter too much, right, for now. And you're doing this integral in momentum, and you have, say, n powers in the numerator, once you already went to spherical coordinates. Even if you have an extra power in the denominator, so you have n plus 1 here, this will still behave like a logarithm at the upper limit, and this will be a divergent integral, right? Now, the condition we're looking for is this, right? So if you go now and you have 2 extra powers into the denominator, let's say you have kn here and k e n plus 2 here. Now this is a convergent quantity, right? This will behave like 1 over k square, right? And will be finite. So this is good, and this is good, and this is bad, right? Now, that tells us that any trick that I can use that increases the power of momentum in the denominator, in the high momentum region, without changing my theory at the low momentum region, will be a regularization. And that's the spirit behind the Pauli-Villars regularization. So that's what we'll do now. So the Pauli-Villars regularization consists in replacing the propagators inside, one or more propagators inside your integrals. In this way, you take, say, a propagator like that, and you replace it by the same propagator plus some new contributions, which I'll write like that. So there's a sum here. I can do this sum. There are many choices that I can make here. So this sum represents that I can put one new contribution, 2, 3, 4, however many are needed, right? And these propagators now, they involve these new scales, lambda I here. So what does this do actually, right? So suppose these AI are negative. That means if I go to very high momenta, right? So K is bigger than both the mass, the physical mass, and this is what sets the scale I'm interested in, right? So if I'm doing physics, trying to describe some particle, I'll be around where this particle exists, right? Near its mass, maybe a little bit above it, but that sets the scale I'm looking at. And lambda is very high above that. That's where I'm making my ignorance parameterize, right? But K can be bigger compared to both. In that case, if these AIs are negative, there can be a cancellation here, and the integrand goes to 0. That's what I want, right? That will regularize my theory. On the flip side, if I am at K much smaller than lambda, all these new contributions will be suppressed by 1 over lambda squared. And they might not matter, and I get back my original theory that is just 1 over k squared minus m squared, right? So essentially I'm subtracting, I'm cutting off the UV, the ultraviolet theory, but now in a softer way. You see, there's nothing here that is breaking my momentum translation invariance. So let's take a look on how this works in the examples in the calculation we're doing. And this is what we're trying to calculate, right? And you see, we already concluded that these, once I go to spherical coordinates and all, this is going like a k to the cube on the numerator, and that means I have somehow to increase the powers into the denominator to 5 or bigger, right? So bigger or equal to 5. Right? What I want to show is that by doing the Pauli-Villars like this, let me copy this sentence here, with just 2 of these new contributions, which I'll call A1 over k squared minus lambda 1 square, and A2 over k squared minus lambda 2 square, right? I can get that. I can get a power into the denominator which is bigger than 5. Right? In order to see that, just think what happens with this sum, right? In the limit that k squared is going to infinity, right? Where the divergence is, right? And of course, I'm always assuming that all the lambda are much bigger than m squared, right? But now I want to see what happens in this limit, right? And keep in mind that I'm abusing the language a little bit when I say this. now that I went back to Minkowski space, right? Of course, these comparisons are tricky in Minkowski space because you could ask, is k squared big, positive big, negative big? You could grow momenta, energy and 3 momenta without growing k squared. So just pretend we are in Euclidean, right? You can go to Euclidean and do this limit analysis. Here I won't use it for anything. I'll do the calculation in Minkowski, and when I need to go to Euclidean, I'll go, right? So keep that in mind. But forgetting that abuse, right? What will happen when I do the product of these denominators? I'll have something on the denominator here, which is k squared minus m squared times k squared minus the first lambda, and then k squared minus the second lambda, and something very complicated in the numerator. If I can choose the a's in the right way to avoid powers of k in the numerator, then this will behave like 1 over k to the 6, right? In the limit I can ignore these mass scales here, right? So that's what I'm trying to get. Of course, now, so this is some complicated here. So now I want to do this properly, right? The first thing is to write the sum of all these 3 terms, right? I'm changing my loop calculation, replacing this propagator by this sum, right? And I have to do the sum, right? I'll spare you the algebra, because this is the answer. There's nothing but algebra here. This is just the product of the 3 denominators here. And in the numerator, what I did is I expanded everything and reorganized in powers of k squared. And the reason I did that is that I want to get rid of these powers, right? This term is fine because it will be something that does not depend on k over k to the 6 in the denominator, but these 2 are not working for me, right? I don't want more powers of momentum in the numerator. So I have 2 conditions here. Happily for me, I have freedom here because I didn't choose the a's, right? And I can do the smart choice. So to get rid of the k to the 4th, I just have to say that this is 0, right? This coefficient here is 0, is one of the conditions, right? If I want to get rid of k squared, then this guy needs to be 0, and now I have a system of two variables, right? A1 and A2, and 2 equations, which is solvable. Again, I'll spare you the algebra, right? It's just solving the system, and the answer is, which now I'll substitute back here in this part, right, to simplify my expression. So this part here, let me copy it. With these 2 substitutions for A1 and A2 here, will be just lambda 1 square minus m square lambda 2 square minus m squared. Again, just algebra. And this turns out to be pretty simple. So what I'm getting at here now is that this substitution here is becoming something. Let me see if I can fit everything like this. So the numerator is this part, and the denominator goes here. Right? So since I know that the lambdas are much bigger than the masses, in those 2 terms here, I can actually ignore the masses. Right? And also, I have still some freedom here, right? I just choose lambda 1 different from lambda 2 to keep it general, right? But of course, these are, again, free parameters, right? Unphysical ones, and I want both to be some big scale. So I can just simplify this and take lambda 1 equal to lambda 2 equal some lambda. We'll just call this lambda, which simplifies my expression a lot, right? this becomes just, let me eliminate this, right? So this one is just lambda to the fourth, right, from these two terms. And here, when I remove this label here, I have the same thing twice. So this is just this denominator square, right? And this is the important result. This is the regularization I'll substitute inside my integral for the one loop contribution, right? And make it finite. Of course, I recover the divergence when I take lambda to infinity, as it is supposed to happen, right? And now you can check that, as promised, this is not changing the infrared part of the theory, it's just changing the ultraviolet, the high energy part, right? You can divide the momentum space in 3 regions. And again, I should really be doing this in Euclidean, for Euclidean momentum, but I'll keep abusing the language here, right? And take k much smaller than lambda, right? Of order of the mass, right? The module of momentum, right? In this case, on this part of your denominator, you can ignore k square, and then you have lambda 4 over lambda 4, right? And so your integrand becomes k squared minus m squared plus I epsilon, like before, right? There's an intermediate region where everything is sort of, k is close to lambda, and then this is really the expression, there's not much you can do, right? And then there's a high momentum region, right, where k is much bigger than lambda. And in that region, now you can ignore lambda here, right? And the mass too, right? And write this guy will behave like lambda 4 over k to the 6, which rapidly goes to 0 for really big k, right? You can even check these numerically, right? And plot these. This is what I did here for some particular number of mass and lambda, right? Notice I choose a cutoff scale which is really close to the mass. Usually you want this to be orders of magnitude above, right? And that's why the region 1, which is here, is so small, right? But I really wanted to focus on the changes. So this is the original. And this is the PV, Pauli-Villars regularized integrand. And you can see, right, you have region 3 somewhere off to the right when this goes to 0, like lambda 4 over k to the 6, right? So you changed really the behavior of the theory up here, right? Starting at some number here, which is really low because I choose a small lambda, right? But at very low energies, right, around where the mass is, you have a theory that has not changed at all, right? So this is what we finally obtained for the one loop contribution to the 2-point function, right? So now it's regularized over here, and keep that result saved somehow. Take note, right? Because we stop this calculation here and resume next video when we get some extra tools in our toolbox to be able to do this integral, which does not look easy, even if it's now regularized. Keep in mind that this equal here has an implicit limit, right? The limit where lambda goes to infinity, right? And that's it for the 2-point function. So now, before we go and do this integral, I want to apply the same regularization method to the 4-point function. So we have both results when we go forward to actually doing the integrals. So let's now apply the same ideas to the 4-point function, right? At second order in lambda, right? These are the three loops that we have to calculate, right? This is the counter term, and now I have to figure out these three guys. Let's take this one first. I label them lambda S, lambda T, lambda U, because they look like a S channel, T channel, and U channel. You see this is goes even deeper, but for now let's just calculate this guy, right? Let me define some momenta here. So the incoming and outgoing momentum, I use same labels I have been using so far. So P1, P2, K1, and K2, right? I'll also use K for the loop running inside the loop, right? And then by momentum conservation on these vertex, it means that on this side I have K plus P, right? Let me write these two better, right? Where P here is just defined as P1 plus P2, right? Which means that P squared is the Mandelstam S variable, which justifies this name, right? And will justify these other two names too. Right? Now that I have defined everything, I can write the Feynman rules for this diagram. So I have two vertices. This is minus I lambda square. I have a symmetry factor here. I have an integral over the loop momentum, 2 pi fourth. And then these two propagators, right? One with k going over there and one with k plus p over here. Let me write both. So this is the top one, it's just k squared minus m squared plus I epsilon. And the other one is I over k plus p squared minus m squared plus I epsilon, right? So that's what I have to calculate, right? And this is just I gamma S at this order. So there's a few things I can say about this guy. First thing is that this has no Laurent indexes to it, right? This is just a scalar quantity. And it cannot depend on k, right? So it can only depend on p. And since it's scalar, this is a function of p squared. So that's the first thing, is that this guy is a function of p squared. And more than that, since p squared in this diagram is equal to s, this is really a function of the Mandelstam S. So this is the first important thing about this integral. The second thing, let me put this down here. The second thing is that it diverges. Again, I can take a look at powers of momentum in the numerator versus denominator, right? And I have something that is d4k in the numerator, nothing else, right? And in the denominator, I have something like k to the square here and k to the fourth, k to the square here and k to the square there. So it's total is like a k to the fourth, right? So this goes like, once you go to Euclidean and spherical coordinates, this goes like Euclidean momentum cubed over Euclidean momentum to the fourth, right? So it's just one extra power into the denominator. That means that if I put a hard cutoff, this will go like the log of that hard cutoff. It diverges less than the previous loop that diverged like this cutoff square, but it still diverges, right? Diverges like a logarithm. Also, you can notice something about these other two diagrams. Let me copy them here. And define momenta, right? Let me put this. So The external momenta are all the same. In fact, they don't enter this calculation because, not directly at least, right? They enter through this combination, but they don't enter directly because, again, these external propagators are not included in the 1pi function, right? So it's the same definition for them, but now I have to define the loop, right? Which I'll define like this k going down and k plus p going up. That means that this expression is exactly the same for this loop here. Same propagators, everything. The only thing that really changes is that for this diagram, P is K1 minus P1. Here, this is K1. This is P1. Right? Which means that P squared for this diagram is just the Mandelstam T, right? And for this guy, right, I can define this momenta the same way. I can put K going down and K plus P going up. But now I have P1 here, and this is K2, right? Because K2 is going out here. This is K2, and this is K1. That means that momentum conservation on this vertex tells me that P is now K2 minus P1. And P squared for this case is just the Mandelstam U, right? That means that I can drop this notation that I put here and just write I gamma 2 as, I just drop ST and U as labels and just call this gamma L, right? L just to differentiate from this guy, right? Otherwise confusion would arise, right? And from the total too, right? The total gamma to 4-point function. And this will be P squared equal S, which I just can put S here, plus I gamma L T plus I gamma L U. Minus, of course, the counter term at this order, right? So if I calculate this gamma L for this S channel loop, right? I'll know this function in terms of P squared, and then I know the other two. I just have to, in one case, substitute P squared for S, in the other case for T, in the other case for U. So I get 3 loops for the price of one calculation, which is pretty good, right? Now, there's something very useful we can do here. Now we can take this gamma L, right, which is a function of P squared, right, and do a Taylor series expansion for it, right? I can write this guy in terms of a series of coefficients times powers of P squared, right? The variable is P squared in the expansion. Yeah. So that, and this is, let me write a generic term here, Bn P squared to n power, right? And Bn, of course, is just the derivative of gamma L of P squared near P squared equal to 0, right? At P squared equal to 0. And so this term right here is just gamma L of 0, and this guy B1 is just gamma prime, the first derivative of L equals 0, calculated P squared equals 0, right? But why would I do that, right? Why would why would I do this Taylor expansion? The thing is that these higher derivatives of gamma are less divergent than gamma itself. right? This can be even used as a form of regularization, right? It's called derivative regularization, but that's not what we're doing here, right? We're just using this as a trick to separate this loop that we're calculating in a part that is convergent and does not need to be regularized, and a part that contains the divergence, right? So before we go forward, let me prove to you that actually taking these derivatives increases the convergence of these integrals, right? First, consider that you can rewrite the derivative of p mu. Take any function of p squared, right? You can write the derivative, the partial derivative in p mu as the derivative of f p squared del p squared times del p squared del p mu, which then is 2p mu up here, del f p squared del p squared, which means, and that's what we want to use, that del f of p squared del p squared is equal to p mu over 2p squared contracted with del f of p squared del p mu. Now let's go back to the gamma L we want to calculate. Where is it? Here, right? I want to take this expression and take the derivative. Paste it here, right? So this is what I'm calling gamma L now, and I want to take the derivative here. So I'll take this I, leave the I there for now, and take the derivative in p squared, which is what appears in my Taylor expansions, right? I'm spending on p squared, not p mu. Now this is this expression, right? Let me do a little bit of simplification. This is a -1 that cancels against the -1 that comes out of here. So I just have lambda squared over 2 up front. And the derivative, I will use this expression. So this goes here. This part I just repeat because there's no, I'm still missing the derivative in p mu, right? But it goes through this integral. I'll just leave here. And then you have right here del p mu of this whole part right here. Okay, let me check. Yeah, that's it. Okay. So now I have to take this derivative. This is not difficult, right? It just acts on this denominator, right? So I get minus lambda squared over 2p squared. There's a factor 2 that disappeared here that came from the derivative, right? This guy just repeats. This one, 2. Let me put this guy into the denominator here. And now the result of this derivative. So this part just becomes the same denominator square, right? There's a -2 that I brought up front. That's why there's a minus here and a factor 2 disappeared, right? And the numerator has this p mu contracted with the derivative of this part, right? So this will be k plus p times p, right? Again, the factor 2 went outside, right? So this is what happened with this expression when I took a derivative in p squared. Now, if you do the same numerator against denominator analysis here, you see that on the numerator I have this, right? Which is the important part, something like k mu here, contracted with other stuff, but that does not matter. And on the numerator I have k squared there, and now a k to the fourth, right? Something like k to the fourth here. So now if I go to Euclidean, the whole story, right? This will be like a k Euclidean to the fourth, because I have an extra power here, but I got 2 extra powers into the denominator. And now this goes like 1 over a hard cutoff, right? So when I take this to infinity, this goes to 0. So the integral converges. And I got that just taking the derivative, right? That means, and this is just one derivative, right? Just one derivative. So if I go back now to the Taylor expansion I was considering, right? I know that this guy diverges, right? This guy, I just saw that the very first derivative makes this finite, right? That means that extra derivatives will only make the convergency better, right? So this whole part here converges, and the divergence needs to be here, right? And that's the point. Now I can write, and this is just gamma calculated at p squared equals 0, right? So now, and this is very useful way of writing it, I'm seeing that I can write gamma L of p squared is equal to gamma L of 0, and this is the divergent part, and the rest of the Taylor expansion I'll call just gamma tilde L of p squared, right? I'm not even truncating the Taylor expansion, right? I'm taking the whole of it. I just separated the divergent part that is given by the very first term in the Taylor series, right? And that's because the divergence was logarithmic, right? If it was a higher power divergence, maybe I would have to take more derivatives before I found a finite piece, right? Also from these equations, so this is very important, let me put a box around it, because now I will calculate these 2 parts, right? The rest of the calculation will be done for these 2 parts kind of separately, right? And the second thing you can get straight from this equation is that I can substitute p squared equal to 0 here, right? And you see that this needs to be equal to this, so there's a condition that this guy is 0, right? So the rest of the expansion needs to go to 0 as p squared goes to 0 too. So again, this derivative regularization can be used in itself, but that's not what I'm doing here. I just used it to justify that the divergence is contained in this part where I calculate this at 0. Everything else is finite, right? So now let's do the Pauli-Villars regularization, right? Again, let me copy again the part that I want to calculate. I'll do it from here. I just have to remove this derivative here. Let me take away everything that was the derivative. And this is the gamma L I want to calculate, right? And I know it's divergent, is logarithmically divergent, and I will do Pauli-Villars to regularize, right? As I said at the start, that there's some choices, right? Pauli-Villars, how many propagators do I subtract? what of here I have two propagators. I could substitute this one, I could substitute this one, I could substitute both, right? And I want to do minimum, take the minimum effort path forward, right? And it turns out that I just need to do the substitution on this guy. That's because the divergence is very weak, right? It's just logarithmic divergence. So any extra power already solves everything. So I'll do Pauli-Villars just for this one guy. That means that I will substitute this expression by this one. And here goes the new piece. In principle, I would have an A here, A1, right? K square minus lambda square plus I epsilon. But in this case, it's pretty clear that if you want a cancellation at high energies, A should be 1. There's no point doing the equations and all because they will be very, very simple. If you need convincing, just put an A here and see what you have to do to eliminate powers of K in the numerator. But this is what does it, right? And of course, I can do some algebra here and put these two terms together, right? This will be just this denominator times this one. I missed some squares here, right? And on the numerator, I'll have just m square minus lambda square, right? After I do some little bit of algebra, right? And this, of course, lambda is much bigger than the mass, so this is just minus lambda square, right? Which allows me to simplify everything. Let me do that. So there's a minus here, so I have minus lambda, little lambda square at front. I have this capital lambda square here, right, over 2. This just repeats. And then I have these denominators, right? First, this one. And then, of course, this one. So I have now this product of 3 denominators. Let me put everything in the same color. Now I can use this expression for gamma L of p squared to calculate both pieces I defined before, right? The divergent and the definite part, right? The first one is just taking p squared equal to 0, right? In this case, I'll get, let me just copy this part here and substitute p squared to 0, right? Again, I'll put a 0 here. Again, there's a little bit of an abuse of language there because I can only go from p squared equals 0 to p mu equals 0 in Euclidean space. But again, eventually we'll go to Euclidean space to finish this integral, so this will be true there, right? Once I do that, this becomes just k squared here, right? Which makes this denominator just the same as this one right here. So I can remove this, put a square right here, right? And as predicted, right, this is the divergent part, because if I take lambda going to infinity, right, then this k goes away, right? This part goes away. And what's left is something that comes here from here, like a k Euclidean cubed, right? Coming from the integration measure, and a k4th, ke to the fourth in the denominator here, and that's a log divergence, right? So that's what we expected, right? And then the second part, which is the rest of the Taylor series, right? I can write the one I called gamma tilde of p squared can be written using this equation up here, right? I just pass this guy to the other side, right? And I get that this is equal to I gamma L of p squared minus gamma L of 0, right? And that's easy to do. I just have to subtract these two expressions up here, right? And that's just this guy minus this one let me change the sign here because there's a minus between them, right? And that I can combine easily, right? I just have to I have this big denominator, right, which is the common denominator here, which I'll call d for now. So let me just write the answer. This is minus small lambda, big lambda, square over 2. The integral, of course, is the same, right? And I'll call the common denominator, just call d. I'll write what d is pretty soon, right? And then I have the numerator, which turns out to be, right, in this case, the extra factor. The first one is a factor of this, right? It's missing here. So it's just k squared minus m squared. I don't have to keep the I epsilons in the numerator, right? And in this second part here, what's missing is this guy, right? So this is minus just this, right? Where d is just the common denominator defined like this. So it's this thing right here times this one. So this is d, right? And so the numerator I can simplify a little bit further. So these masses go away, right? There's a factor k squared here, right? So this is just k squared plus 2k p plus p squared. And this k squared part goes away with this one, right? So in the end, I have I gamma tilde L of p squared is equal to minus, let me copy this, all of this, just to make things faster, times that numerator that's just, there's a minus here, so minus 2k p minus p squared, right? So that's the expression I wanted. So let me put a box around this guy. Also, very importantly, I got this one. And of course, in this case, you can see, right, so that this is finite. If you do the same analysis we've been doing again and again here, you'll see that D here, right? If I take this guy and take the limit of lambda, you recover the divergence by taking lambda to infinity, right? If I do this here, I can ignore this k here, so this it goes to infinity like minus lambda square, right? Which means that there's a minus lambda square overall minus lambda square into the denominator, which conceals with this lambda square here, right? So and that means that gamma tilde L of p square, when you go lambda goes to infinity, right? I can rewrite this guy just as there's a minus 2, so this will be just this thing. Let me erase the box, right? It will be just this thing, or times this numerator and this denominator. Which, if you do the high k analysis, right, here I have k Euclidean cubed times this k, so a total of k to the 4th in the numerator, and a k, here I have 4th, here I have square, so a k to the 6th in the denominator, right? So I have shown this for the first derivative term. Now I'm showing for the whole series, right? You see it converges as the fastest. I mean, the highest power of lambda is really the first one, so that's how it behaves at high momentum. So now the bottom line is we have to save, again, like you did for the 2-point function, right? You want to keep that expression in mind, and this one, because together they give you the one loop calculation for the 4-point function, right? And again, I have to do these integrals, right? D is defined up there. And that's what we're doing next video. There's a lot of tricks we'll have to learn in order to do these integrals. And these tricks are the same, very similar, for the 2-point function and the 4-point function. So we're doing everything at the same time, right? So save these two expressions for later. And that's it for today. Thank you for your attention.